All right, I'm recording the second lecture for 113. So last time we ended at slide 17, lecture 13, right? That's what we did last time. So we discussed conservation momentum, right? And then whenever you see collisions in a problem, you're going to use momentum and impulse instead of energy, because there are many forms of energy involved in a real collision. It's very hard to use conservation of energy to make predictions, right? But there's one special type of collision which we can make very precise predictions, which is the elastic collisions, right? That's what we discussed last time. An elastic collision is a collision where the kinetic energy is the same before and after the collision, which is very rare in real life, right? Truly elastic collisions only occur in atomic or subatomic scales, okay? So that's why elastic collision is very important in a physics experiment, right? This theory. But in real life, collisions between two very hard objects are very close to elastic collisions. So then we can go ahead and use these two equations derived from conservation of energy and conservation momentum to make predictions. So if you see elastic collision, you see these two keywords, and then you want to make any prediction during that collision, okay, after the collision especially, go ahead and use these two equations, okay, and then these two equations, they're going to be given, right? You don't need to remember these two equations. They have already been derived from conservation of energy and conservation of momentum. So they're not a new law. They're just a very special conclusion from conservation of energy and conservation of momentum. Okay. Now, first of all, today I want to tell you that conservation of momentum did lead to a very important discovery in the history of physics. Okay, so let's take a look at the slide 18. The question. Okay, it's a long story, but let's really carefully get all the information we need. A neutron is an electroneutral subatomic particle with a mass just slightly greater than that of a proton. Okay. A free neutron is radioactive and decays after a few minutes into two subatomic particles. Okay, when it decays, it just becomes two particles. In one experiment, a neutron, a rat, was observed to decay into a proton and electron. Okay, and they were shot back to back, always, right? We discussed this last time. And in order to conserve momentum, they have to be moving in opposite directions. So one momentum is positive, the other one is negative. You add them together, you will get a zero. Now we have the masses of the proton and electron. We also have these two velocities. Okay, let's assume, of course they're going to be moving in opposite directions. Let's assume the proton is moving in the positive direction. We want to find the total momentum of the proton and electron after decay. Okay, so how do we find the total momentum? So this is what happens. This is the neutron. So it's going to decay into a proton and an electron, right? The proton is going to go this way, the electron is going to go that way. We know these two velocities, right? The proton has a velocity, this number. Okay, and then the electron has a larger velocity. So we also know the mass of these two guys, right, from the problem. They're constants. We're going to assume this guy's moving in the positive direction, and then we want to calculate the total momentum of the proton and the electron after the decay. Okay. In this case, I don't even need to use a law, right, because I just want to find the total momentum of this system. I just find this momentum and add them together, right? And momentum, it's always mass times velocity. Now, should be careful. They are moving in opposite directions. You need to take that into account. Assign them the correct signs. That's why the problem even said that assume the proton is moving in the positive direction, right? So if you want to find the total momentum after the decay, which is the final, right? You're going to do momentum with the electron plus the momentum with proton, okay? Assign the correct signs, okay? Add these two numbers together. So I would call, so the problem says, let's call this guy positive. Now I'm going to call this guy negative, right? So the electron, final velocity of the electron, you should plug in a negative number. You're dealing with vectors, okay? All right, and the masses are given. You put all these numbers in with the correct sign. You will find the right answer is B, okay? You put all the numbers in. Okay, so, okay, this is a simple problem. Why do I want you to do this? So, I want you to think about the energy and the momentum in this process. First of all, let's take a look at the energy, right? Do the numbers violate conservation of energy? Slide 19. Okay, let's take a look at the energy before and after the decay. What is the, let's take a look at the kinetic energy. What is the kinetic energy before the decay of the system? Before the decay, they are just like one particle, right? They're together. The neutrons are around. What is the total kinetic energy? Still. What is the final kinetic energy? Well, you can calculate that. Right? You just do 1/2 mv squared plus 1/2 m proton final squared. Well, I'm not going to calculate the number because it's got to be a positive number. Because both of them are going to be positive, right? Kinetic energy, the square is going to take, even if you want to assign them signs, the square is going to take care of that negative sign. Now, if you compare the kinetic energy before and after the decay, you get some kinetic energy, right? These two particles, they get some kinetic energy. Does this violate conservation of energy? Think about it. This does not, right? Because we have done that before, right? You can't just compare kinetic energy, right? If you want to test, if you want to check conservation of energy, you have to calculate all different forms of energy in this process, which is usually very hard. Okay, then you compare the total number before the process, the total number for the energy after the process. You compare these two numbers. You only calculate kinetic energy. You can't just say that, okay, these two numbers are not equal, energy is not conserved. There are other forms of energy, right? Where does this energy come from? Look at, let's go back to this process. Initially, the kinetic energy is 0. Final kinetic is so these two guys looks like they get some kinetic energy out of nothing. Now, in this case, this kinetic energy comes from the nuclear energy. Okay, that's the very famous equation Einstein discovered. Okay, so actually, if you calculate the mass very carefully, the sum of these two masses is going to be a little bit smaller than the mass of the neutron, okay? And that mass has become the energy, nuclear energy. That's why these two guys get kinetic energy, okay? Conservation of energy is still true here. These numbers, they don't violate conservation of energy because you only calculate, if you only calculate kinetic energy, you can't say conservation of energy is violated. You have to consider other forms of energy. In this case, some nuclear energy has been converted to kinetic energy of these two particles. Okay, so that's good. Now, what about momentum, right? Slide 20. Do these numbers violate conservation of momentum? Let's take a look at these two, the momentum before and after. After the decay, we just found the momentum, right? What is the initial momentum of the proton, of the neutron? Well, again, it's not moving. It's 0, right? Because you just do mass times velocity and it's not moving. Now let's compare these two numbers. Initial momentum is 0 before the decay. After the decay, the final momentum, well, it's a very small number, but it's definitely 0, right? And it is a significant number in that scale because we're talking about the proton, electron, and neutron, right? So this is a significant momentum. Then the total momentum of a system is not a constant before and after the decay if you compare these two numbers, right? Looks like these two guys, they get some momentum after the decay. Even if I take into account the sign, I will get this, okay? Does this violate conservation momentum? Initially, the momentum is 0, total momentum. Finally, the total momentum is not 0. You don't have these two numbers equal. Do these numbers violate conservation momentum? Think about it. The answer is yes, okay? Because momentum is only m times v. We don't have different forms of momentum, okay? You can't say there's some nuclear momentum converted to the momentum of this proton and electron. No, there's no such thing. Momentum is m times v, then that's it. We don't have different forms of momentum, okay? If you want to calculate momentum, just do m times v. That's it. Only one term, only one form. Then what is wrong here, right? So why does this violate conservation momentum, okay? If these are the two numbers you get from the experiment, yes, these numbers, they do violate conservation momentum. That's why, if you go to slide 21, this experiment was repeated like many times in the 30s, okay? And a lot of physicists, they repeated this experiment, right? One said, okay, looks like my experiment violated conservation momentum. Some people were saying, no, maybe you did a mistake. Let me do the experiment. And they got the same numbers, right? Well, not the same numbers, but they got the same conclusion. The total momentum before and after decay, not the same, okay? So it looks like conservation momentum has been violated in this process, okay? So, but we do have a very strong belief in these fundamental laws, conservation laws, right? So in order to fix that, Pauli, okay, proposed a solution. So he said that maybe there was another particle, a third particle, produced in this process, okay, but we were unable to detect them, right? Why? Because, you know, when you do a physics experiment, right, you're dealing with these little guys, right? So you're gonna be super careful that you're gonna take into account every detail, every particle produced in this experiment. So he proposed that there must be another particle, a third particle, produced in this process, but it was like, we didn't detect that particle, okay? And then this particle was named neutrino, okay? So the name means little neutral one, okay? And then say if you accept that assumption, right? There's a third particle, neutrino, going that way, and then this guy's gonna again contribute some negative momentum, right? If you call that positive, and then you add these three momenta together, you will get a 0. So momentum is conserved. So that's his solution. Okay. So he proposed this should be what happened in all these experiments. And neutrinos, they were indeed discovered about 20 years after his prediction. So the reason people didn't discover neutrino in the 30s is because neutrinos, they're very, very light. They're almost massless. Okay, see that something's almost massless, it's very hard to detect. So that's why these experiments in the 30s, they all missed that particle. So they thought, okay, conservation of momentum has been violated in this process, but no, it wasn't violated. It's because there was a third particle, very, very light, okay? So we were unable to detect that. After 20 years, physicists were able to detect that particle, and then you add all these momenta together, momentum is still conserved. Initial 0, final also 0, okay? So you see that conservation momentum has led to a very important discovery in physics, okay? All right, so that's the experiment I want to discuss with you. Now let's go to slide 22. So we have learned many laws, but we didn't learn like 1,000 laws. As I said, there are only a limited number of laws in physics, especially in mechanics. So what laws did we learn, okay? And then if I see a problem, which law do I pick to solve the problem? When you see constant force and constant acceleration, so the law I would try is going to be Newton's laws and kinematic theory, right? Kinematic equations. Why? Because kinematic equations, they are for constant acceleration motion, right? And then sometimes the problem doesn't tell you the acceleration, you need the acceleration. Then you use Newton's laws to find the acceleration, right? You set up Newton's second law in x and y, you find the acceleration, you plug it into kinematic equation. So that's what I would do when I see a problem with a constant forces and constant acceleration in that problem. So I would try Newton's laws and kinematic equations, okay? And then when I see things like when the forces and acceleration of the object in the problem is not a constant, especially like, there are like objects, like a system with many objects, okay? So that's a very complicated process. I can't use Newton's laws or kinematic equations. Then I would consider energy or momentum. Then when do I use energy? When do I use momentum? When I see things moving at different heights, and when I see a spring, okay, 9 times out of 10, I would just use work and energy. Why? Because if object move to different heights, most likely I can have the gravitational potential energy involved, right? So mgh. And if there's a spring, I can use elastic potential energy, right? So when I see objects moving to different heights, and there's a spring in this process, so I would try work and energy. Then when do I use momentum impulse? When I see collisions, right, explosions, right, recoil, decays, right, that's when I use conservation of momentum. I use momentum and impulse to solve the problem, okay? These are the theories we have learned so far. We didn't learn like 1,000 theories in physics, right? But we did practice a lot of problems, right? Okay? So physics is always like that. Pick the right law and then do the math, okay? Very carefully. Don't just draw any conclusion based on your judgment, right? It's very hard, especially when the problem is very complicated. It's not intuitive at all, and you want to find a number, right? You don't do that intuitively. It's not that obvious, like A is going to be equal to B, B is going to equal to C plus D. No. You pick a right law, you do the math. Sometimes it's going to take you some time to finish the math until you get the right answer. And that math is also going to guide you. Maybe I'm missing something, so I need to use another equation, okay, to find the thing I need so that I can continue in this law and then find the right answer. Okay, so pick the right law, be patient, do the math. The math is going to lead you to the right answer. Okay. Now I want to do a final problem in this part, which is going to have both energy and momentum. So this is a good example where we're going to use 2 different theories in one problem, because this it's a very complicated process, and we can actually do the experiment. Okay, this is an experiment we're going to do. Okay, this is also a very classical experiment in working in energy and momentum. So let's take a look at this. So experiment is this. Okay, okay, I do have a if you look at the slide 23, the question is this: if you drop a tennis ball, right? Or actually any ball, right, from a certain height, and you drop it, it's going to fall, it's going to hit the ground, then it's going to bounce back. But it's not going to bounce back to the original height, because during the collision, some kinetic energy is going to be lost. It's going to be converted to other forms of energy, right? So it's not going to carry the same kinetic energy and then reach the same height, right? So you can always do that, right? So if I drop at this height, right? So it's going to bounce back very low, it's not going to bounce back to its original height. You can do that with all kinds of balls, right? Like a basketball. You do this, and then you drop it at a certain height, right? It's always going to bounce back very low. Okay. Now we're going to do, this is intuitive, right? We're going to do an experiment like this. What we want to do is this. What if I put the tennis ball on top of the basketball and then drop this system. So how high does each ball go? Okay, are they gonna still like behave like just one ball? They're just gonna bounce back to a lower height, or they're gonna behave differently? So that's a question we want to answer. So we're gonna first do the math. So this is a complicated process. This is not intuitive at all, right? I don't think anyone has done this experiment in their life, right? You put a ball in top of another big ball and then let them drop. No. So this is not intuitive at all. You don't have experience with these things. That's when you use math, right? Math is a more reliable guide to the answer instead of common sense or experience or simple logic. Okay, so let's do this. We're gonna first make the prediction, then we can test the prediction using these two balls. Okay, so this is what we want to do, right? So we're gonna first drop these two balls, let them hit the ground, and then they bounce back. We want to find how high they're gonna bounce. Each ball is gonna bounce back. So we're going to divide it into 3 different processes, okay? Because this is a rather complicated process. You can't just solve it in one step. So we're going to break it into 3 processes, okay? So the first process is this, right? When you drop these 2 balls, both of them are in free fall, right? You drop them, so you can consider them as one system. They're gonna drop and then to the ground. So this is free fall. And then I'm gonna find the velocity both of them carry just before they hit the ground, right? So free fall, I know how to do that. Either I can do kinematics or conservation of energy, right? Now, and then they're gonna collide with the ground. So this is a collision, very complicated. And then after that, they're gonna bounce back. So we're going to break it into 3 different processes, okay? So let's start with the first one. So I want you to find the velocity of the system when they reach the ground if both balls are dropped from 1.2 meters, okay? So now you can just, because it's free fall, right? You consider them as a system. Then you can either do kinematics or conservation of energy using the numbers, okay? So I want you to try that. And then we can compare our answer, okay? I can't have you do a clicker, but pause the video, do the work with me, and then compare your answer with my answer. Okay? So now let's see. I'm going to use conservation of energy because I know that a lot of people, they always use a kinematic equation. That's the most familiar theory that you don't be afraid of using new theories, okay? Conservation of energy, I would do this, right? And only these 2 forms of energy are involved. And then conservation of energy, 1/2 mVf squared minus 1/2 mVi squared. That's the changing kinetic energy, right? Changing potential energy, mgHf minus mgHi. And then only gravity is on it, right? After I drop them, I will get a 0. So now let's plug numbers in. So this is going to be initial point, this is going to be final point, right? Because this is the first process. Free fall. Okay. Now, initial velocity is 0, right? Because they're dropped. So I would have 1/2 mv final squared minus 0. Final height is going to be 0, right? Because they're going to reach the ground. Okay, so I only have 2 terms in this equation. Rearrange this equation, you can find the final height, right? So the final height is going to be 2hi. No, I'm sorry. And square root. Well, again, you will get plus and minus, right? In this case, well, you can get plus, but just remember this is down, right? So in this case, you plug numbers. So the initial height is just going to be 1.2 meters from the problem because they dropped from 1.2 meters. Okay, so this is 1.2 meters. No, right here. Okay, you plug the numbers in, you will get, I'm going to keep the, and this negative sign just means that, right? Or you can just say the velocity is, you don't use the negative sign, you just say the velocity is 4.85 meters per second. Understand? Okay? So the first part, easy, free fall, right? Free fall, you see that you can either use Newton's law conservation or kinematic equations or conservation values, right? Now we're going to move on to the collision. So the collision is rather complicated, okay? So even the collision, we're going to break it into two different collisions, okay? Because now I'm going to, no, let's draw it there. I'm going to draw it large. So the basketball actually is going to first collide with the ground, right? And the tennis ball is still falling, okay? So everything happens really quick. Everything happens really quick. I'm going to break it into two different collisions, okay? This guy is going to collide with the ground first, the basketball, right? So we're going to assume that's an elastic collision. I know that after this collision, the basketball is definitely going to reverse direction, for sure, right? Because that's what happens when the basketball collides with the ground. It's going to reverse direction. And of course, I know that when it reverses direction, it's going to lose some kinetic energy, right? Because when you drop a basketball, it collides with the ground, the velocity is going to get smaller, the kinetic energy is lost, right? Some of the kinetic energy is lost. That's why it doesn't bounce back to the original height. But now for simplicity, let's just assume the basketball first collides with the ground and then reverse direction really quick, but keep the same velocity. Okay? So, well, this is not true in real life, but again, we just want to make a prediction and then test the prediction, okay? Now, then you see that this happens really quick. The basketball collides with the ground, reverses direction with the same velocity. Now it's going to move up. And then at the same time, the tennis ball is still falling, right? Okay? It's still falling with 4.85 meters per second, right? Still the same speed, right? But now the basketball has already finished the collision with the tennis ball, right? Or with the ground, I'm sorry. Then they're going to collide again, right? So this is the second collision, okay? So everything happens really fast. You can't even tell there are two collisions. But now we want to find we want to make a prediction. So we should be very careful. We're gonna work on the details, okay? So this is the second collision. So basically, the tennis ball is still falling. The basketball now is moving up because it has already finished the collision with the ground. Now that's the second collision. This collision is also very complicated, right? Any collision in real life is very complicated. We already simplified the first collision between the basketball and the ground. Now we're going to also simplify the collision between the tennis ball and the basketball. We're going to assume it's an elastic collision. Okay, now you see these two keywords. Elastic collision. When you see elastic collision, what do? You plug numbers into these two equations we learned, right? And these two equations, they're going to be given. You don't even need to remember them, right? What are these two equations? These two equations are this, right? So V1F, they're on slide 14. M1 minus M2 divided by M1 plus M2 V1I plus M2 divided by M1 plus M2 V2I. Right? Now the second equation, see, I don't even remember this equation. There's no point in remembering these equations, right? 1I plus M2 minus M1 divided by M1 plus M2 V2I. Okay? That's the second process. Now we're working the second process. Actually, there are two collisions. Now let's see. Do we have the numbers? So, okay. Let's call the basketball M1. So this is M1. Let's call this guy M2. So the problem gives us M1 is the basketball, 590 grams. Okay? So convert it to SI units. Now M2 is the mass of the tennis ball, 57 grams. Okay. Now, what about these initial velocities, right? You need V1i and V2i. So now you're going to be careful, right? You're working with velocity, they have direction, especially in this case, basketball is moving up now in the second collision. Tennis ball is moving down. Even though these two numbers are the same, but they're in opposite direction, how do you take that into account? You assign them the correct signs, okay? If you don't assign them the correct signs, you will get the wrong answer. So what I'm going to do is this, right? V1i, that's up, okay? I still call up positive. V2i is down. Now I'm going to call it negative. Okay, now I have all the numbers I need, right? Now I can plug numbers in and then find out the V1f and V2if after these two balls collide, okay? So do the algebra carefully, put numbers into these two equations. So then, okay, again, pause the video, do the algebra, okay, see if we can get the same answer. If you do the algebra very carefully, okay, with all the correct signs, in the second process, you will get V1f, which is the basketball, okay? So this is the basketball. After this collision, it's going to have a final velocity and positive, okay? So that means that the sign is telling you after this collision, the basketball is actually move up. It's not going to move down, okay? Now the tennis ball, V2f, you plug all the numbers in. You actually get a very large number, also positive. So both of them are going to move straight up. Okay? So that's what happens. Okay. Then it's going to be the third process. Now both of them are going to move up. Right? So are they going to collide again? Right? Because this guy, the tennis ball is now moving up. Now the basketball is also moving up. But the basketball is slower than the tennis ball. So that means the tennis ball is going to go very fast. So the basketball is not going to catch up with the tennis ball on the way up. Okay, so that means after that, they have already lost contact. They're not going to be in contact with each other anymore. It's in free fall. Both of them are in free fall, right? So this guy is in free fall with this velocity really fast. This basketball is also in free fall with this velocity. A little slower than that, right? But both of them are going to in free fall. In free fall, how do you find the maximum height they can reach? Okay, free fall, you can still do kinematics or conservation of energy. Okay, so that's the third part, slide 25. Okay, so let's do that. Okay, then we can compare our answer. All right, so now let's do the algebra. I'm going to still use conservation of energy. As I said, conservation of energy is my favorite law in physics 1. Okay, set it up. This doesn't change, right? Now you see that now the rest is going to change. Now both of them are going to move up. So I'm just going to work with one object, right? Something moving up, and then it's going to reach a maximum height here. So this is the initial point. This is the final point. The final velocity is going to be 0, right? Because that's the top, very top. Initial velocity, leave it there, okay? Now the final height is what I'm trying to find, right? So I'm going to leave it there as the top, very top, the maximum height that this object can reach. Initial height is the ground, right? Because both of them start with the ground. So that's going to be 0. All right, so in this case, don't forget what we're doing. We're trying to find final height, right? Something moves up straight up with some initial velocity, and then I want to find maximum height it can go. So you rearrange this equation, you will get final height. It's going to be so this, you move this term to left, so you will get 1/2 okay, so it's going to be this. Vi squared divided by 2g. Right. Okay, that's it. All right, now you see that, and this is going to be true for both the basketball and the tennis ball, right? Because they're just going to lose contact. They're going to move it separately. They're going to be moving separately in free fall. So all you need to do, just plug this. Now these two velocities are going to become the initial velocity for them in the third process, right? So in the third process, now I can use this conclusion, right? So for basketball, the final height, now you're going to plug this velocity as the initial velocity and square divided by 2 times g. Right, so you will get, okay, again, do the algebra, and then we can compare our answers. And then you do the same thing with the tennis ball. This is going to be the initial velocity in the third process. Plug it in. Okay. Now that's our prediction. Okay, even though we made some simplifications, but we can still see how high they can go, okay, quantitatively. Remember, they have been dropped, so initial height for each of them is going to be 1.2 meters. So this experiment, both of them are going to be dropped in at 1.2 meters. After all these collisions, everything, they're still going to bounce back, right? The basketball is going to bounce back to 0.5 meters, so lower than that, even less than half of that, which makes sense, which is intuitive. Even if you just drop one basketball itself, it's just going to bounce back very low, right? Because it's going to lose some energy during the collision, lose some kinetic energy. But the tennis ball is very interesting, right? The tennis ball actually is going to bounce back much, much higher even than the initial height, right? Initially it's dropped at 1.2 meters, and then after all these collisions, the tennis ball is going to bounce very high, like 8 meters, okay? So is that true? We can do the experiment, right? Okay, we did make some simplifications. We assume that there's no kinetic energy lost in this process, and then this is also elastic potential energy, no kinetic energy has been lost. So in real life, the tennis ball is not going to really go that high, but you can still see that the tennis ball is going to go much, much higher than the original height, okay? So that's our prediction. Now I can do this experiment. If you have a basketball and tennis ball at home, try that, okay? Now, well, okay, I don't know if you can see that because this guy is going to just go out of the video, I guess, okay? But anyway, I'm going to try. And then this needs some practice because when you drop this basketball and the tennis ball together, first of all, you're going to make sure they're aligned in one vertical line. So that's already hard. And then when you drop that, a lot of people, like even myself, tend to do this, tend to pull the hand this way, right? So you have to drop it totally vertical. And that's really hard because usually you can do this or even like this, okay? So then you will see 9 times out of 10, because you're going to get some movement in horizontal direction. So you may see the tennis ball go that way or this way, like that. But still it's going to go bounce very high, okay? It's still going to go very high. But if you can get them move only in a straight line, so this tennis ball is going to go very high, okay? So let me try that. Okay, see if I can get it just moving in a straight vertical line. Okay. Good. You see that? Well, I guess you didn't see the top, okay? But it bounces very high. And then I also attached a video, a link to a YouTube video where a girl did this experiment. This is a classical experiment. The name is called stack the ball experiment. So you stack a few balls together, okay, one on top of another. So the more you stack, the more balls you stack, the higher the ball at the very top is going to bounce, okay? So in that video, the girl used the 3 balls, okay? And after all these collisions, the ball at the top is going to bounce really, really high. You can check the video. It's really, really amazing, very impressive. Okay, so again, to summarize, we use this experiment to practice both conservation of energy and momentum in one problem. This is a very good exercise, right? When do I use conservation of energy? When do I use conservation of momentum, right? Check this slide 22, right? So that's the general rule. That's how I find the correct law. And sometimes, if the problem is very complicated, you don't just solve it using one law, right? You may need to pick different laws. Like in this question, I broke it into 3 different processes, but for the first and the third one, they're just free fall. So I can use kinematics or conservation of energy because I see different heights, right? So I can get MGH involved. Collisions, when you see collisions, you always use momentum and impulse. You don't use anything else, unless it says elastic collision. Well, elastic collision, it's even easier. You don't even need to pick a law. They have been derived. Just go ahead and use these 2 equations, okay? All right, so we have finished. You will get many problems on the homework. Do these homework problems, okay? Practice these problems. Work and energy and momentum. They're definitely harder than Newton's laws and kinematic equations, okay? All right, so we have finished lecture 13. Now I'm going to move on to the next topic. Lecture 14, okay? So now we're going to move on to a different topic, totally different topic, rotations, okay? We're going to discuss rotations, because rotations, they are very different from straight line motions, so that's why we want to discuss. And then I have to warn you, this part is the hardest part in Physics 1, because nothing is intuitive. Nothing is intuitive. Even though we do see rotations a lot, we never really think about rotations, right? We never really try to make predictions in the rotations, okay? So, and then in this part, so all these laws we're going to learn, they're very non-intuitive, okay? And we're going to define a lot of weird things, okay? And then the key is this, again, first of all, you're going to see a lot of connections between rotation and the straight line motions, linear motion. Use the connection to help you understand this part. Secondly, practice. Whenever you learn new theory, right, practice and practice, then you will get used to it, okay? So, okay. So for rotations, okay, we usually use angles instead of distance to describe a rotation. Why? For example, take a look at this bike wheel. Right. If I'm rotating the bike wheel and I want you to tell me the distance, any point, I pick a point and ask you the distance that point travels. Well, that's going to be different, right? For example, if I pick a point here at the outer edge, well, okay, if I rotate this guy, then that point is going to travel a larger distance than the point I pick here, right, to rotate the same, in the same period of time, right? Apparently, any point close to the center is going to travel a shorter distance than any point at the edge, right, in the same amount of time. So if you use distance to describe rotation, you always need to specify the point you're referring to, right? And not always, we always refer to the edge, right? Sometimes we're interested in something moving, not just on the edge, right? Any random point, okay? So it's very inconvenient if I want to describe something has rotated like 5 meters, 10 meters, okay? Always need to specify the point, okay? Especially it's a whole object rotating. So any point you pick on this object, they will always travel a different distance, okay? But if you just take a look at the angle, right, then every point is going to travel, is going to cover the same angle. For example, pick this spoke. Any point on this spoke, when it's rotating in the same amount of time, every point is going to travel the same angle, right? If this guy travel, a point here at the edge travel like 30 degrees, and this guy has also traveled 30 degrees, right? So every point on this rotating object, if this guy has finished one full rotation, right, now let's pick this point. It's easy for me to remember. Every point has traveled 360 degrees, okay? So that's a nice thing. So that means if I talk about rotations with angles, then I don't need to specify a point. I would just say, okay, it has rotated like 90 degrees. Then you know what I mean. Because every point on this rotating object is going to travel 90 degrees. Okay? So that's why we use angles instead of distance to describe a rotation. It's easier. Okay? And what is the SI unit for angles? Okay? If you remember that, that's the radian. Okay? That's the radian. Okay? It's not the degree, even though we use degree a lot, right? But degree It's not the SI unit for angles. All right. So, and then what is the definition of radians? If you still remember that, so if there's an angle, okay, like this, okay, so it's part of a circle, this is an arc, you can always define the angle in radians using the arc length and the radius. Okay, you divide the arc length by the radius, you will get the angle. And it doesn't really depend on the radius, right? Because you see that if you make a big circle with this angle, you will get a bigger, larger arc length, but you also get a larger radius. So the ratio is still going to be the same. Okay, so you always get a unique number. Now, and you see that if you do this, what is the SI unit for arc length? Meters, right? That's a length. What's the SI unit for radius? Oh, that's still meters. Okay, both of them are going to be meters. So actually, if you do arc length divided by the radius, you get a pure number. You don't get any unit, right? So this guy in radius doesn't even have any unit. Okay, so radians, strictly speaking, is not a real unit, okay? Because you get a pure number here, okay? But to distinguish with the normal number, we still call it radian. But radians is not a real unit, okay? So, and then how do you convert between radians and degrees, right? It's like when you have meters and miles. I know that miles is not the SI unit. But if I want to convert meters to miles or miles to meters, there's a way to do that, right? I just need to know the conversion. So the conversion between the meters, between the radians and the degrees, that's very easy to figure out, right? You don't even need to remember that. Just think about one revolution, one complete circle, that's going to be 360 degrees. I know that, right? Everyone knows that. If you don't know that, you shouldn't be in college. Then what's the corresponding radians for this, right? So let's use this definition, right? So for a full circle, you're going to do the arc length divided by radius, right? Then you can get the radians. What is the arc length for a full circle? That's just the circumference, right? Circumference 2 pi r. And this divided by this. So that's going to be the conversion between them, right? 360 degrees is going to be equal to 2 pi radians. Very easy to figure out, right? If you understand the definition of radians, okay, you don't even need to I'm going to remember that, okay? So that's the definition of radians, okay? So now you see that the angle is pretty much equivalent to the distance in linear motion, right? So, and then when something's rotating, I want to describe how fast it's rotating, right? I can define something similar to the speed, right? How do I describe how fast something's moving in a straight line? We define this thing, distance over time, so that we call it speed, right? So then I don't need to use words. I just calculate the number. I can say this thing is moving at 5 meters per second, that thing is moving at 10 meters per second. We can do the same thing. We can define something called angular speed, okay? We'll use this Greek letter omega. It looks like a W, but it's a Greek letter omega. So we're going to use a lot of Greek letters in this part. Now compared to this the definition, now I'm just going to do changing angle divided by changing time. So this guy is going to tell me how fast this object is rotating, right? And of course the unit is going to be radians per second. Okay, so that's this. Now, and then we also define something called acceleration in linear motion, right? Because sometimes we want to even know how the velocity is changing, right? Something is accelerating, getting faster and faster. I want to know the rate, okay? So this guy is defined as changing velocity divided by changing time. We can also define a thing called angular acceleration, okay, for rotations. So we use this Greek letter alpha. So now I'm just going to use changing the angular speed divided by changing time. right? So that tells you how fast the angular speed is changing, right? So now the angular acceleration is going to be in radians per second square, right? So you're going to see a lot of connections. We pretty much are going to define the equivalent of every variable we define in linear motion in this part, so that we can still use the laws and theories we learned in the linear motion to solve problems in this part, okay? And then strictly speaking, these two guys, because velocity and acceleration, they're vectors, right? These two guys, they're also vectors, but the direction of these two vectors, especially this guy, is not that intuitive, okay? So the direction of the angular velocity, it's very weird. You see that if something is rotating in a horizontal plane like this, I'm rotating this guy, so I can calculate the angular velocity, right? But actually the direction is going to be perpendicular to the plane, right? So if this guy is rotating that way, I'm going to use my right-hand rule to grab this rotating object. My forefingers are in the direction of the rotation. My thumb is in the direction of the angular velocity. So if this guy is rotating that way, the angular velocity is actually in this direction. Isn't that weird? Very weird, very non-intuitive. But again, the only reason we do that is that that's the only way you can make a complete and consistent theory out of it, okay? But in this class, we're not going to really worry about that direction, okay? So you don't need to worry. We're just going to focus on the magnitude. And the direction of the angular acceleration, that's more intuitive, okay? Because the acceleration is going to be the direction of the acceleration, but still, it's going to be either this way or that way. But once you find out the direction of the angular velocity, angular acceleration is easy. Then if the angular velocity is increasing, the acceleration is the same as the velocity. If the velocity is decreasing, the acceleration is opposite to that, which is the same as the relation between these two guys, right? When something is accelerating, that means acceleration and the velocity are in the same direction. When something is slowing down, acceleration is actually in the opposite direction. So that's more intuitive than angular velocity. Okay? So, but in this class, we're still just going to be focusing on the magnitude. We don't need to worry about the direction. Okay? I'm going to stop here.